Okay, all of them are material master students. Okay, early part of your career. So I want to hear from some of you before I start anything. What are your dreams? At least one or two of you, can you just tell? Sir, this is what I want to be 20 years down the line. You are all, I suppose, must be around 20 years old now, right? So when you all reach around 40, around the age of Prakash, let's say, what is that you want to be? No one has any dreams?
Sir, I'm Vishwakannan from DJ
Yes.
Vaishnav College.
Yes, Vishwakannan, tell me.
I'm from DJ Vaishnav College in my first year MSc Physics, and 20 years down the line, I wish to be some sort of researcher, a good researcher. My field of interest is
I'm happy that you have changed the statement. You started with some sort of researcher and then said good researcher. Okay?
Yes, sir.
So I don't want some sort of researchers. Okay? I don't think some sort of researchers will do any good to the country. Okay?
Yes,
only good researchers will do good to the country. Okay, good. Anything else? So that's what is your dream. And
yes,
anything
sir.
more?
My field of passion is astrophysics, and
Wonderful.
I think our country is only starting to create dominance in that field. So if I could learn things from other countries where they've done and bring back the expertise here to India, it will be useful. That's what I wish to do. Some students, I wish to, when I become a professor, I wish to inspire some students to get into the field and strengthen the country there.
Perfect. Perfect. Thanks a lot, Vishwakannan. Happy to hear that. Anybody else? I see a lot of people. I see one Ranjini here. Ranjini, you have any thoughts?
Sir?
Yes, tell me.
Sir, I'm not sure of anything, sir. From 20 years now.
It's too long to think.
Yes.
Huh?
Yes. I would like to do something that I love.
What do you love? You still don't know what you love.
I haven't figured.
At 20 years age is the time to even decide who should be the Prime Minister of the country, right? So you are being given a chance to select who should lead the country. When you can select who should lead the country, you should also be able to select what do you want to be, whether you want to be a leader or not, in whatever field it is. That's I think it's the right age to start planning your future. Anyway, so this is my suggestion. Just keep this in mind in future. Okay. Anybody else?
Good evening, sir.
Yes.
I'm Priyadashri from Madras University, and my ambition is to become a professor so that I can show my uniqueness and my teaching. What are the opportunities or the ways I must to learn so that I can implement in my teaching to make students so interesting in the subject. It's what my ambition.
Happy to hear that. This is exactly what I thought when I was 20 years old. Okay. Okay. Anybody else? One or two more, and then we'll come back to the topic. Anyone? Okay. Have you all heard? Read about a book called Ignited Minds? Anytime?
Yes, sir.
Is this book familiar to you? How many of you have read this book? Can somebody raise your hands? Whoever has read this book, at least can you speak out and saying that, yes, I have read it? Unmute yourself. No one has read this book among these 40 students who are sitting here? That's, I would consider that not a good thing, okay, for the country, I would say. It's important, all your physics, chemistry, everything is important. It's also important to read some good books. And this is one of those best books. I have at least given this book to a lot of kids of your age, asking them to read this. Okay, this book is, do you know who has written this book? Anybody among the audience other than Prakash and Prabhu? No one knows.
Abdul Kalam, sir.
Very good, very good. So, have you read this? The two students who have mentioned Abdul Kalam's name? No, you have not read.
No, sir.
Please go back and read. It's worthy to buy this book. It's just about 150 rupees. Okay, it's much less expensive than a pizza that you eat. Okay, so please buy this book, and it's going to change your life. I can tell you, it's going to change the way you think about life. He talks about dreaming. He says everybody should dream, and the dream should be as colorful as possible. That's exactly what he says. And a person who doesn't dream will never be a leader. I can assure you this. If you want to be a leader one day in your life, you should learn to dream. Okay, and only people who dream and pursue those dreams are the ones who will become leaders. Otherwise, you will be simply a follower. Okay, it's easy to follow. Okay, very, very easy to follow, but it is not easy to be a leader. To be a leader needs a lot of perseverance, a lot of determination, and a lot of what I would say courage. Okay, and courage not just to pursue something, courage to accept failures. There are so many failures that each of us will face. In my life of 55 years now, and a professional life of about 30 years now, okay, I have failed a number of times. And every failure teaches you something. A leader accepts those failures and learns from those failures and moves on. And this is something I request all of you to adopt this particular concept into yourself, and then you will be able to. If somebody says I never failed in life, I would say you have never learned anything in life. So with those few words, sorry for taking your time into a non-technical topic, but I felt at that age of 20, these are important. What subject you learn, astrophysics or not, that is less important than whether you put your heart into that or not. Okay, so that's very important. Whatever you choose, your heart should be in it. I always tell to my students this: a good researcher should have three qualities. I say, one is, if assuming that some of you will do a PhD at some point of time, I always say this, that one is you should be able to go for a cup of tea with your friend and talk only research, not talk about a cricket match or a movie that has come yesterday. Second, you should be able to go to bed thinking about the research problem that you are solving. Okay. Third, you should be able to catch hold of a 12th standard kid and make that person excited about what you are working. That can only happen when you are excited about what you are doing. I'm thoroughly excited about anything that I do. Okay, so that's the reason why I sleep very little. 4-5 hours is what I sleep every day, and so much of excitement. Every day is an excitement. There's so much to learn in life. At this 55 years of my age, I see so much to learn, and you should be much more enthusiastic than me at your age of 20. And science and research can be a romance. Okay, you love it so much that every day you feel so much of excitement in a love that a 20-year-old kid feels it. Okay, and that's something which I feel when I work on these particular fields which I'm going to talk about. So what I thought is today talk to you about what is exciting about nano. Every one of you must have read about nano at some stage or the other, and possibly some of you are also doing projects in nano, and also possibly are thinking of even doing a PhD in this particular field. So let me take you into this world which is so exciting. Okay, and just to tell you that the nano is not just confined to our research labs. There are so much of products which are nano products that are coming out. There's so many girls I see here, and some of you must be using a lot of cosmetics. I think boys also use cosmetics nowadays. So there is so much of nano in these cosmetics. Whether it is a hair dye that you use or whatever it is, there is so much of nano involved into it. Starting from a toothpaste that you use every day morning, whether it is Colgate whitening or Pepsodent whitening, you already use nanoparticles. To a water purifier that you use, to space technology, or even your laptops and mobiles, everywhere you see this embedded into your life to an extent that nowadays you can't think of life without nano. Okay, we are every day using so many products which have nano in them. Okay, including medicines for that matter. So how did this whole thing excitement came in? Okay, people were always excited to see small things, okay, and play with those small things to design certain products which can be significantly different from what the usual products are by making them at a small scale and seeing whether such a small scale can lead to a significant improved properties. And in that direction, there was always an attempt to see small things. Okay, and there are microscopes that have been developed. This is one such microscope, which is called AFM, atomic force microscope, where if you put your hand below that microscope and keep on magnifying it, you will see various things starting from blood cells to the level of a DNA and even the molecules in the DNA. All this is possible to be seen. And to the extent that people can even see atoms. When I was in IIT Madras, we used to have microscopes. Even at IIT Hyderabad, we have. Only thing is I don't get enough time to bring students and show. I used to bring school children and show them how exciting to see atoms in front of your eyes. Okay. Of course, when I say atoms, these are images of atoms, and there are microscopes like this. The one that is there on the screen. This is called Titan. Okay, the Titanic that you all know. Okay, it's almost similar to that, and which costed us about 20 crores, where you can actually see atoms in a metal. Okay, this is silicon. What you see at the bottom right is, let me see if I can have pointer. Okay, so what you see here, this is nothing but silicon atoms in a silicon chip, for example. So we can see every white dot that you see is an atom. Okay, so it's possible to see atoms very easily. It's also possible to see atoms in every material almost. For example, what you see on the left side, you see certain white dots which are arranged in some kind of a lines. Okay, these are what we call them as atomic planes inside a material. And there is a small region where there are dots, but these dots are not arranged in any specific manner. So this is what we call it as an amorphous material. Okay, where there is no periodicity and complete randomness. Okay, so to the extent that you can have materials, this is what you have on the top left is a quasi-crystal, we say. So you have a five-fold symmetry in these quasi-crystals. When you carefully look at these dots and look at them, you will see interestingly pentagons. Okay, just to tell you that materials can have a variety of atomic arrangements, and this is one such thing with special periodicity, which we call it as quasi-periodicity, and special rotational symmetries, which are called five-fold symmetries. We can also talk about seeing atoms in 3D. So I will show you again a little later where how we can see atoms in 3D using fantastic microscopes such as what we call it as atom probe tomography. And all this were driven by people who wanted to see what happens when something becomes very small. For example, take a big boulder, okay, and break it into small things. Or go to Marina Beach, simply pick up the sand and you look at the sand particles. Each particle is of the order of around a millimeter in size, or a little half a millimeter or something like that. If I take that particular powder, put it into something like a Sumit mixie, okay, and grind it to very fine size, such that the particle becomes, let's say, 100 nanometers, 50 nanometers, 20 nanometers, 10 nanometers. What happens? You see fantastic changes in properties. One such property change is optical properties. Okay, for example, gold. Many of the girls sitting here wear gold chains. The glittering yellow color of gold comes only when the grain size inside the gold is large in size. The moment the grain size inside the gold chain, somehow I make it very small to around 50 nanometers in size, it actually becomes greenish in color. If I take it to around 25 nanometers, the gold becomes reddish in color. If you actually make gold about 10 nanometers in size, gold actually becomes black in color. So the yellow gold that you all know can be completely black in color just by changing the particle size. So this has been somehow experimented by people. People made such kind of sizes of particles. For example, all these images that you are seeing on the left and right, these are all paintings on glass, windows in most of the old churches. And all these have been basically, people call them as emulsions. People have embedded nanoparticles into a glass, and depending on the size of these particles, people get various colors. Okay, even Faraday, who is well-known scientist, was supposed to have worked on these so-called colloids. People call them as colloids, and this is possible with every material. For example, this what you see, these different colors in these test tubes kind of thing, are all same material, simply silica, just the sand in a marina beach. Okay, just bring it down to small sizes and different sizes. You put them into a container with water. So suspend it into water. You will see different particle sizes give you different colors. And just same material can give you different colors. So now people talk about what is called, band gap tuning. Okay, people are all talking of OLEDs, optical LEDs, and LEDs of different colors. All this is possible by simply changing the particle size of a material, and different sizes give you different optical properties, and you get different colors. And this also has been well known long back. Okay, even in India, for example, people seem to have made wonderful materials with such materials. For example, many of us talk about the Delhi iron pillar. People call it as rustless wonder. So this is something very fascinating for an Indian, that this is nothing but a piece of steel with a height of around almost 30 feet or so, which has been made of steel, and it has never rusted in almost 500-600 years so far. It's a pride of India, I would say. And similarly, another pride of India was making the steel itself. Steel was first made in India. It is called ekku in your Tamil, and it is called ukku in Telugu, for example, my own mother tongue. And people found that it is a very strong material, that it can cut a helmet into two pieces. So people used it as sword. Alexander the Great, all those great people, samurais, they all used this sword, and the technology went from India to various countries. Somebody took a small piece of that from a museum, put it into a microscope, a high resolution electron microscope, and saw nanostructures in them. You can see these lines that people still debate whether these are carbon nanotubes or whether they are carbon nanowires. There is a lot of debate on that. But what is interesting is that there are nanostructures in such a sword. And people now believe that such a high strength that comes in these materials could be because of these nanostructures. But how did these nanostructures enter into it? Whether the people at that particular point of time, 2000 years back, knew the whole technology of making nano materials is a question that we do not have an answer now, but there are so many people excited to go and learn these things. So there is a lot to learn from our history. And people also got excited about it in the modern world, starting from a gentleman by name Feynman. Possibly some of you physicists who are sitting here should know that people call him as the best physics teacher ever born on this earth. Feynman, okay, and a very famous teacher, and of course a Nobel laureate. He talked about how to manipulate things at a small scale. So he was talking about there's plenty of room at the bottom. What he's talking about is manipulating at the atomic scale so that you can design new materials. This is a lecture given in 1959, and what people have now done after about 30 years after he talked about it in 1990 or so, people are able to write miniaturized writings onto certain background on some substrate. For example, what you see here, each of these white colored letters are as small as about 50-60 nanometer sized letters, and we use something called atomic force microscope to see these letters, magnify and see them. And this is done by a technique called nanolithography, and many people are using it. And this is something that he could not do it at his time. And he talks about it. If you see here, he says, people tell me that there is large prayer that can be written on the head of a drawing board pin. Imagine in your college a notice board where there are pins that are put. The diameter of it is approximately 1 centimeter or so. Can we write the whole Encyclopedia Britannica on that? And people say, yes, it is possible. You just need to miniaturize your letters and you should be able to write the whole Encyclopedia Britannica on one single drawing board notice board pin. And people can now utilize microscopes to see them. He even went to the extent to say, can I arrange the atoms the way I want? And this is exactly done in 1990, again using scanning tunneling microscopy, and that gave a Nobel Prize for that microscope itself, where people are able to lift atoms from somewhere and put atoms where they want. What you see here, IBM, every dot that you see here is an atom, that people are able to lift atoms and arrange atoms. And he actually talked about it in 1959, that can we arrange atoms the way we want? And that is something which is something realized after almost 30 years or 40 years of research after he has talked about it. And all these have become very popular, and people are trying to learn a lot of things from the nature. And for example, one such thing that people have learned is to look at the nature, and there are so many interesting things in the nature. For example, the lotus leaf. You put a water droplet there, it doesn't stay there, it simply drops off. So the so-called, what people call it as super hydrophobic nature. How did this super hydrophobic nature came to this particular lotus leaf? So somebody pulled a small piece of this lotus leaf and put it into a scanning electron microscope, and he was able to see that there are what are called nano spikes in this material. And because of those nano spikes, when you put a water droplet, because of the capillarity, everything is pushed and it comes out. And people are now utilizing. And similarly, this water strider that you talk about, it walks on water, but the water does not get stuck to its feet. Again, this is again super hydrophobic nature, comes because of what are called nano spikes in its feet that are available. People are now trying to use this for what is called self-cleaning coatings. People, for example, if in Chennai, there are so many buildings, if you go to Mount Road, where there are all glassy buildings. Okay? And in this all glassy building, how do I clean on a daily basis? It is not going to be so easy. And so many cars are going, and so much of what is called unburnt hydrocarbons that are coming out, emissions we call them as, and they go and get deposited. You see a stain, colored stain on that, oil marks on the surface of this glass. Can I clean it somehow? And people now say that if I can have a nano coating, it will be able to see that all the dust particles, water droplets are simply drop off because of the capillarity issue. In addition, if that particular nano coating is of a special material such as nano titania, it has what is called a photocatalytic activity property, because of which a hydrocarbon that gets deposited on it in the presence of sunlight or in the presence of some light, it can split the hydrocarbon into hydrogen and carbon. And the hydrogen will react with the oxygen of the atmosphere, carbon will react with the oxygen of the atmosphere, and both of them vanish into the air. And as a result, the whole stain is removed automatically on its own. So this is what we call it as self-clean glasses. Again, all the nanotechnology is being used for such things. Now, how do we make such nanomaterials? Okay, so far we talked so much exciting about these nanomaterials, and I'll talk more about these excitements as we go along, but more important also to know how do we make it. Some of you who are already working on it might know it. So typically we say there are two ways of making it, two broad classifications. One is called a bottom-up approach, another is called top-down approach. Bottom-up approach basically means start from atoms, bring atoms together and make them into a cluster, and do not allow this cluster to grow to bigger size. And that is what is called bottom-up approach. There are many such techniques, what we call it as wet chemical techniques. In chemistry, you can make certain ingredients react with each other, and a nanoparticle can be nucleated out of this reaction because of some atoms coming together and forming. This is one possibility. Another possibility is in physics. People talk about PVD, CVD, physical vapor deposition, chemical vapor deposition, where you can evaporate something and everything is in the form of gas, and the atoms in the gas are allowed to deposit onto a cold substrate and ensure that during the deposition, you do not allow these deposited particles to grow to bigger size, and you get nanoparticles. So there are so many such ways, which are all called bottom-up approach, where you are starting from atoms and getting into nanoparticles. There is another way where you start from bigger things, break them down to smaller size into nano. I told you about taking a Marina Beach sand and putting it into something like a Sumit mixie and grind it to make it into nanoparticles. And this is what we call it as top-down approach. And in my lab, mostly, we utilize this particular approach called top-down approach, and we try to make everything broken into nanomaterials. And how do we do that? There are techniques such as this. We call it as a high-energy ball mill, okay? Where it is nothing but a container which has powder. I put, let's say, Marina Beach sand into it, and I put some balls into it and rotate it. And in the process, the balls are going to hit the powder, and when the powder is hit by a ball with a high energy impact, then the powder breaks. And in the process, you will see that materials become nano like this. And every particle, black dot that you see, okay, if you look at a scale here in an electron microscope, this will tell you that each of these particles is of the order of around 10 to 20 nanometers. And this kind of particles can be generated easily by this kind of a technique. Almost everything can be broken. Even polymers, people have tried. They can break them into small nanoparticles by this kind of a technique. And you have to find out what is the energy that I need to impart to convert a normal material into a nanomaterial. And once you get such a nanomaterial, there are many interesting properties. One such thing is, because I'm an engineer, that too an engineer called materials engineer, we are interested to make materials which are very strong materials. Okay, so for example, aluminum is a very soft material. But if I can make aluminum into nano and embed some particles into that nano, for example, some kind of compounds, you must have heard of various compounds in material science. And if I can take an aluminum matrix and put some compounds such as what is called Al3Fe, and such kind of nanoparticles, if they are embedded into aluminum, you get a hardness as high as 12 gigapascal. 12 gigapascal means 12,000 megapascal hardness, which is much higher than what is the hardness of a typical aluminum. Aluminum usually is very soft. You can take an aluminum rod and bend it with your own hands. Okay, it has a strength of 50 megapascal. I'm talking of a strength which is almost like about 5,000 megapascal or 5 gigapascal. These are all possible just by making some particles very small. So the strength can be significantly improved. You can do variety of things. For example, if I'm trying to in chemistry, I'm doing some reactions. Okay, I can enhance the reactions in a chemistry by simply making it nano. You all know that in any reaction, if the surface area of a material is large, then the reactions are much faster. For example, catalysis, we know. If a material has a very small particle size or a large surface area to volume ratio, the material has a large reactivity. Exactly the same thing we have done. By when you want to extract metal out of a ore, We simply take the ore and put it into a ball mill like this, make the powder particle size extremely small, and using what is called an acid leaching technique. Typically, if I use acid leaching technique on the powder particles which are of the size that you see in a, let's say, Marina Beach, you get a recovery, metal recovery, which is 10%. But I simply take the Marina Beach sand and let's say I convert it into a much finer size by 2 or 3 hours of ball milling, and I get a recovery of metals by the similar acid leaching technique, almost close to 100%. From 10% recovery, I go to 100% recovery. This is just because I'm enlarging the surface area so that the material can easily react with others. Okay. Similarly, we can also utilize this large surface area for what is called sintering. If you have a powder, if I want to make a component out of that, what do? I bring the powder, put it into a die and a punch and press it so that powder becomes like a brick for you, which we call it as a pellet. And if I want to make powders such as tungsten into such a small piece, okay, it is not going to be easy because just by pressing, the powder particles do not come. I have to heat the powders to high temperatures, and there is a technique called sintering. And when you use that sintering, then you can make a component out of it. And for tungsten, people use tungsten as a filament. The light that you have in your room possibly will have some tungsten there. Okay, and this filament is made by heating the tungsten powder at temperatures as high as 2800 degrees centigrade. Then only tungsten gets sintered, because tungsten melting point is 3200 degrees centigrade. So what we have simply done is taken the tungsten powder, ball milled it for about 2 to 3 hours, and that particular tungsten now is a nano tungsten, and you can sinter it at 1600 degrees centigrade, as low as 1600, which is still high for some of the applications. But when you compare with 2800 degrees centigrade, the energy that you need to spend is going to be much lower when you are able to sinter it at much lower temperature. So this is something in Trichy. There is a plant called heavy alloy penetrator plant, okay, where they make tungsten pieces. And what they do is they simply take these pieces and throw them onto enemy tanker. They are called kinetic energy penetrators. Defense people use it for that purpose. Simply like a bullet, it will go, because of simply half mv square is the kinetic energy of anything. And if the mass is higher, then the energy is higher. When will the mass be higher? For a given volume, if the density is higher, mass is higher. Tungsten has 19.3 density. When compared to that, aluminum has a density of 2.7. So instead of an aluminum piece, if I throw a tungsten piece, it will have a much higher energy. And this is exactly they do. And they were facing problems that the energy that they have to spend to sinter this tungsten powder to make a kinetic energy penetrator, which is nothing but like a small bullet, okay? And they found that the energy required is very high. Now we have been able to demonstrate to them that you need much less energy, and they are able to save a lot of energy. Like this, we can do so many things. One more thing, we can make a material very tough by making it nano. For example, in your own Chennai, okay, Avadi, there is something called CVRDE, where they make what are called armor plates for what is called tankers. If you have ever seen any tanker like Arjun tanker in Google or so, you would see that in front of it there are steel plates, okay, which will prevent any bullet hitting this tanker, okay. But the problem is they were using steel, and whenever you weld a steel, people found that the welded joint is so weak that if you fire a bullet, it pierces through the welded joint. So it does not have enough toughness. It does not absorb energy. They need something which will absorb energy of a bullet that is coming. We said you can simply take steel and do some processing and create nanostructures in the steel. If you look at the top left, you see the micron marker. We call it as micron marker. This shows that this bar is about 20 nanometers. That means each of this what is called plate kind of things that are there inside have a thickness of about 20 nanometers. We call this as a nano steel. Okay, a steel with a nanostructure inside it. And such a steel has a high toughness. We call it as high energy absorbing capacity. Now with that steel, when I make a plate, weld it, you will see that not only the plate, but also the welded joint is so tough. You fire a bullet, nothing happens. Okay, it doesn't penetrate anymore. And this is now being used by the defense people for their applications. And one can also do variety of coatings. Being a material scientist and a metallurgist, we make steel in huge quantities. Tons of steel is made by melting of steel in steel plants. Okay, you have a Salem steel plant in Chennai, and there is a JSW Jindal steel plant, and so on and so forth. Okay, and all these steel plants have large containers called ladles, which are nothing but a container made up of refractory bricks. Okay, like the bricks in your home walls. And these bricks, when you bring take liquid metal at 1600 degrees centigrade, and so that this particular ladle holds this particular liquid metal, there is a lot of wear and tear. And people have found this being a big problem, and very frequently you have to change the refractory bricks. We said just simply give a nano coating on that bricks. This is exactly what Prakash worked with me when he was a postdoc in my group earlier before joining the Madras University, and he was able to demonstrate with his own intellectuality that we can simply give a nano coating on these bricks and increase the hardness from 48 Vickers hardness to 780 Vickers hardness. And we were able to demonstrate that you can increase the life of these refractory bricks almost 2 times. Okay, double the life, which is very important. And many people are interested. Now we have a project which we are trying to get from Jindal Steel. We did this for Vizag Steel Plant, and so on and so forth. One can do a variety of things. This is another where I was talking about self-cleaning glasses. A glass which is coated and a glass which is uncoated. If you look at this glass here at the bottom, part of it is coated, part of it is not coated. You cannot even make out the difference at all because the coating thickness is 50 nanometers. And each nanoparticle inside that is about 10 nanometers in size. Such nanoparticles can be coated, and you cannot even make out that it is coated, and it can give you wonderful what is called self-cleaning property. A lot of people are excited. This is a project that we did with a lab called ARCI in Hyderabad. Now this has been transferred to an industry, this whole technology, and the industry is trying to make such kind of coatings in a large scale. We can also demonstrate that materials which are usually used as electrical conductors, okay, such as copper. Copper is a good conductor, but unfortunately copper is very soft. Can I make copper strong without losing the conductivity? So again, we demonstrated that if you make it copper nano and somehow ensure that the nano is retained, you would be able to demonstrate that you can have almost 3 times the strength of the regular copper without losing much conductivity. These are all very exciting things one can do. One can also demonstrate this in various other cases. You can also have reactions happening inside the ball mill, almost at room temperature. You must have seen people trying to reduce an oxide with a metal. And whenever you try to do this, you have to heat the what is called a mixture of these two to be able to reduce. Whereas here, in this kind of a technique called ball milling, you don't need to heat anything. Everything happens at room temperature just because the particles have become nano. So the reactivity enhances. And we have demonstrated that any oxide can be reduced by another metal very easily with this kind of a thing. And many interesting things can be done, and all that happens below a certain particle size. For example, when we reduce like that, for example, if I take a nickel oxide, reduce it by aluminum, I get nickel and alumina. If I can control my composition carefully, I don't get just pure nickel. Nickel plus aluminum, a compound called NiAl I get, and I get an alumina as a product. So both of them are called a composite now. You have NiAl, you have alumina, it's called a nano composite because both of them are in a nano state. And such a material has a very good strength and a very good what is called toughness inside the material, because it's what is called compressive strain is very large. And these kind of materials are very useful for what is called coatings, where you want a very high wear resistance coatings. For example, if you are using specs nowadays, you go to a shop to buy specs, they all talk of coating on your specs, wear resistance coating, scratch proof coating. Okay, this kind of coatings are all obtained by this kind of nanotechnology, where you give a very fine, thin layer of coating, and that gives you very high wear resistance, so that your specs will be scratch proof. And this is all can be done with this kind of coatings. One can also embed nanoparticles into metals and demonstrate that they can have very good properties. We worked with IGCAR Kalpakam. Some of you possibly are aware of it in Chennai, 50 kilometers from Chennai near Mahabalipuram. You have this Indira Gandhi Center for Atomic Research. They have been now moving into what is called fast breeder reactors from their conventional reactors. And in a fast breeder reactor, the temperature generated during fission reaction is very large. And as a result, normally they use a steel to make a tube like this. What you see here is like a tube. This is called nuclear fuel pin, which is like a tube in which you put the nuclear fuel and put it inside the reactor, and then now there is a reaction that is taking place, fission reaction, let's say, and there is a heat that is generated. Now, this particular steel is useful up to 500 degrees centigrade. The moment you cross 500 degrees centigrade, this steel with 9 chromium and 1 molybdenum will not work. So what we have done is taken nanoparticles of yttrium oxide, embedded it into steel, and we call it as oxide dispersion strengthened steel, ODS steel. And now you are putting oxides into it, okay, and these oxides will make the steel very strong, so that even when you go to 700 degrees centigrade, the steel will be still stronger. A normal 9 chrome 1 moly steel will not be strong at that temperature. And this is now, we have been able to make such tubes with the help of what is called DMRL in Hyderabad, NFC in Hyderabad, and this is something which is a fascinating project, where we have been able to demonstrate that this material has very good creep properties or high temperature strength resistance. Now, if I have such a material with nanoparticles embedded in it, can I see them? Can I find out the composition of this thing? And now we have such microscopes available very close to your ACT campus on the other side of the road. In IIT Madras, we have this facility called National Facility for Atom Probe Tomography. This whole thing costed 40 crores for us. Okay, and what it does, it can show you, this is what you are seeing, something rotating there. It is nothing but a sample, image from a sample. This is like a CT scan. Okay, three-dimensional image from layers of 2D images, which are all stitched together to get a 3D image, where each dot is an atom. All the pink dots that you are all seeing is iron atoms, because this is steel, basically iron atoms. And these green kind of particles that you are seeing are all about 2 nanometer sized yttria particles. Now I want to find out what is the composition of it. Is it Y2TI, Y2O3, or is it having any other elements inside it? Okay, what is the stoichiometry of that compound? I can easily find out by doing this atom probe tomography. This is something which is a fascinating, no other technique can give you a composition of something at such a small scale. And this is a facility which we have set up by getting money from various sources. 6 IITs have given 2 crores each, and government has given the remaining about 25 crores. ARCI, something in Hyderabad, gave it 2 crores, and Baba Atomic Research Center gave me 2 crores. And with all that, we have set up this facility which can be remotely operated. This is the beauty of it. In the whole world, this is the first remotely operable atom probe tomography technique, where you can send a sample to us, we polish the sample, put it into this atom probe. What you see on the top left is what is called an atom probe. Okay, and it is called LEAP, local electrode atom probe, we call it as. You put the sample inside, and then somebody sitting in IIT Bombay can operate this. You just need to have this kind of a workstation, what you see on the table here, with the software loaded, and IIT Bombay sends a sample to us, and we put the sample inside, and the IIT Bombay person sitting in front of the computer, he can operate this particular microscope and collect all the data. And this is something which is a beauty of this thing. First time we have been able to do it, and we run it in 3 shifts. I have 3 operators who come and run it in 3 shifts, 24/7. Possibly this is the only microscope I can proudly say in the whole country which runs on a 24/7. Okay, and that's the beauty of this microscope. And this has been running last 2 years. We have almost 40 papers, very high-end papers that have come out in this particular 2 years on this particular microscope. So many people using it. Some people even from abroad are coming and using this machine. It is very fascinating. And just to see, tell you, how does it show? Okay, for example, this is a steel, the same steel I was showing you. If I look at how iron is distributed, this is called elemental mapping of iron, elemental mapping of tungsten and chromium. You see all of them are uniformly distributed. But if I look at what is the mapping of yttrium, titanium and oxygen, you see that yttrium and titanium and oxygen are inside these particles. And that's why we say this is a particle made up of what we call it as Y2Ti2O7. We have been able to establish the composition of this particle by knowing the composition of the particle, by analyzing this data. All this is possible. I would take maybe about 5 more minutes to tell you another exciting field in material science that is coming up, okay, which has become very popular in the last 15 years, where people are making a cocktail of material. Okay, for example, what happens if I take 5 different elements and add them in equal proportions and make an alloy out of it? Let's take a simple example, like have you heard of barium titanate any time? Anybody? Any oxide that you are aware of? No? Nobody? Okay, so barium titanate is one of the piezoelectric materials. Okay, just for your information. Okay, lead zirconium titanate. Yes, PZT we call it as. That is also a good. So now, if I take a PZT material, okay, and I dope in the lead site a number of elements, and I dope in the zirconium site a number of other elements, I make a kind of khichdi of this whole thing. If I can say, use a word like that, and I make a compound now, which is containing, let's say, 5 or 6 different elements inside it. And what we see is when you add so many elements into it, the randomness increases, which we call it as entropy. Okay, the material will have a high entropy when you add so many elements. That's why we call these materials as high entropy materials. Okay, if you make it in a metal alloy, we call it as high entropy alloy. You can make a high entropy oxide, you can make a high entropy carbide, you can make a high entropy boride, you can make any of such high entropy materials. And these high entropy materials have very fascinating properties. We started working on this. The first paper in this field came in 2004, and we started in our group working in 2005, and now by now a lot of people have been working on this. We already brought out 2 books in this. 2014 we brought 1 book, 2019 we brought another book, which is the updated version of this. So many papers, almost 5,000 papers have been published by now in this particular field, just in 15 years. Okay, such a fascinating field. And such an alloy can be made in nano form. This is a nano alloy which has 6 elements: aluminum, iron, titanium, chromium, zirconium, zinc and copper. And each particle that you see, nanoparticles, that black dots that you are seeing, each of them have all the 6 elements inside it and in equal proportions. If you divide 100 divided by 6, you will get 16.6. So if I have a piece of material in which 6 elements are there, equal in proportion, you should have 16.6% of each of them. And if I take any particle and put an electron beam on that, by a technique called energy dispersive spectroscopy, I can find out these elements present and their composition. You can see each of them is very close to 16%. 16, 15, 17, just within 1% error. Okay, the composition is so uniform. And such a material can be made, and it has wonderful properties. We can also use atom probe to see how uniform these elements are. Okay, you can see every element is uniformly distributed, no segregation at all. Absolutely, it's such a wonderful uniform mixture of all these elements at the atomic level. Very, very important to see. Okay, and that is possible to achieve, and these materials have wonderful properties. One such property we have found, this is recently patented by us about 2 years back, that it has an oxidation resistance which is much better than any of the metals that are known. Okay, some of the best metals for oxidation resistance is called superalloys. Okay, and this is better than even a superalloy. Okay, and this is a work that we did jointly with a Deakin University in Australia, and one of my students, Rahul, worked on it, and this is a fascinating thing. And one can use these high entropy alloys as coatings and demonstrate very interesting properties. I'll not go into the details of it. I can also show that you can make materials with very interesting functional properties. For example, we know a metal typically, okay, when I heat a metal, what happens to its resistivity, electrical resistivity? Anybody knows? Most of you are in physics and chemistry. So
decreases.
It increases or decreases?
Decreases.
Decreases.
Somebody says increases, somebody says decreases. What should I do?
Decreases.
Decreases.
Decreases due to thermal ejection. The electrons will move randomly.
What is decreasing? Is it conductivity decreasing or resistivity decreasing?
The conductivity decreases.
I asked you resistivity. Okay, so resistivity increases with increasing temperature. This is exactly what you see, this particular curve, the increasing resistivity as a function of temperature. Okay, a typical metal such as aluminum, copper, iron, it will have such a thing. The moment I make this alloy in a nano form, what we call it as a nano quasi-crystalline form, a special structure it has, immediately you see a reverse trend that is happening. Okay, the conductivity is now suddenly, resistivity is decreasing with increasing temperature. That means the material has almost become, a metal has become like a semiconductor now. Okay, this is the behavior of a semiconductor, we all know. So I can change the configuration of materials. Okay, convert a metal which has overlapping bands and make it into a material with a separated band structure. Okay, just by making it into an interesting nano structure. So, and now I can even change the band gap, and people are playing with this in a nano structures. Okay, what we call it as tuning the band gap. I can tune, you can tell me this is the band gap I want. Okay, because band gap decides the various colors that can be produced, right? All of you know this. So I can make different colors out of this. Lasers of different colors are coming up nowadays. All this is happening because you are able to make materials with different band gaps, and all this can be done. And we can make materials with interesting properties. Okay, this is one such piezoelectric material called lead zirconium titanate, PZT, and by making it nano, suddenly its dielectric properties significantly changes. We can demonstrate that this material, this is a PZT material. Usually a PZT material has a dielectric constant of the order of 2000. The moment I make it nano, like this, each particle is very small, 10 nanometers in size, and its dielectric constant is 35,000. What is the advantage of this? We have seen that this material, once it has such a large dielectric constant, you can ensure that piezoelectric materials have a special property that if you compress the material, it produces electricity. Okay, for example, a microphone that I use to speak, my voice is getting converted into an electrical signal. Okay, and the electrical signal is once again converted into a voice sound signal. All this is happening because of a piezoelectric material there, and the piezoelectric material is converting the sound wave, okay, into an electric signal. And now if this piezoelectric material is a nano piezoelectric material, the conversion efficiency is much higher. So what we have done is we can use it for what is called energy harvesting. We worked with something called ARDE in Pune, where if you can make a piezoelectric powder and make it into a compact, something like a 1 rupee coin, and put that coin in your shoe and start walking, you can generate electricity. And have a wire going, and you carry a battery, let us say, the battery can be charged. And this is exactly being used now by soldiers, okay, where they use these piezoelectric pellets in their shoes, and by the evening as they walk, they can charge their battery so that their night vision goggles can be charged by this particular energy that you are harvesting. So you are harvesting the energy. The fascinating thing. People can actually make this material in the form of a mat and put it into a big Phoenix Mall, for example. And as thousands of people walk, you can generate electricity by the evening. Okay, so like that, a lot of fascinating things can be done. And I'll just go to two such more examples of what kind of interesting properties can be achieved. For example, magnetic properties. I can take a ferromagnetic material, one which is a hard magnet, another which is a soft magnet, make a composite of these two, and make a nano composite of these two, and I can demonstrate that we can have a large hysteresis loop. Many of you know that a soft magnet has a very thin loop, a magnetic hysteresis loop. For example, it looks like that's number 2 that you see here. Okay, it has a high permeability but a very small coercivity. But a hard magnet has a low permeability but a little larger coercivity. But if I make a nano composite of both these, now my permeability increases when compared to a hard magnet, and my coercivity also increases when compared to a soft magnet. So I have both the worlds in my hand. It is like having a cake and eat it too, as people say. So I am able to make a material with a large area under the hysteresis loop. What is the advantage? It makes the memory devices much more capacity. What people are talking about, terabyte memories that people are talking about, all these are possible with this kind of what we call it as exchange coupled magnets. Okay, these are called exchange coupled magnet, where you have a soft magnet and a hard magnet. There is an exchange coupling that takes place between the two magnets, and as a result you have a large energy storage capacity. Okay, and people are using it for big computers. Are all supercomputers are utilizing this kind of a technology. And I can make a material which is a magnetic material and a piezoelectric material, a combination of this. For example, a ferrite, such as a nickel ferrite NF, is a magnetic material. Many of you possibly know. And a BT, which is a barium titanate, is a piezoelectric material. I can make a composite of these two in a nano form, and we call this material as a magneto-electric material now. It will have both magnetic property and ferroelectric properties, or piezoelectric properties, and you can have a combination of these two properties. And this is again very, very fascinating thing. And by taking a material to nanoscale, you will be able to. And there is a parameter that people use to measure this, how good a magneto-electric material this is. It is called alpha parameter, what is called magneto-electric coefficient. And this magneto-electric coefficient for such a nano composite is extremely large. And we have been able to demonstrate that you can make such kind of wonderful magneto-electric materials which have a large magneto-electric coefficient. So like this, I can go on for hours together to tell you how exciting materials can be made. I mean, this has been a journey for me, starting from my PhD days about almost 30 years back. And all these 30 years has been such a wonderful journey. And what I have been showing you is possibly the work of at least 20 different PhD students. Okay, so there's so much that one can do. I think with that, I will stop now. If you have any questions, feel free to ask me. I think there's another material, so multiferroic materials can be done. I will leave it there. Okay, any questions that anybody has?
Thank you very much, sir. Students, you may interact with our professor. Switch on your mic. You may interact. If you have any doubt, you may get...
If you have any doubts or questions or clarifications, feel free. I have 10 more minutes time for you. I should leave by 6:15.
Good evening, sir.
Yes, ma.
This is Bhuvana doing second MSc Physics at Jayapals College, Chennai, sir.
Yes, Bona.
That was a very nice and very good lecture, sir. I feel I gained more information about nanoscience and technology, sir. My question is, you told about high entropy alloys. What is the use of that high entropy, sir?
Yeah.
Why we go for that high entropy?
Very, very interesting question. Thank you for asking such a good question. Usually, materials, okay, in metallurgy, we talk of materials which are ductile and brittle. For example, if you have a cup like this, like I drink coffee, I drop it. What happens? It breaks into pieces, right? This is nothing but a ceramic material. I call this as a brittle material, okay? And most of the compounds are brittle, okay? And the reason is they have ordered structures. Materials which have ordered structures, chemically ordered structures, have high strength, but they are brittle. They break easily. And materials which are disordered structures have possibly high strength if you can play with the composition and structure. At the same time, they are not brittle. Okay? So by making a structure into a disordered structure, I am bringing in a toughness into the material. Okay? For a metallurgist like me. Okay? So if I usually materials, what happens is, if I take let's say sodium chloride. Sodium chloride is a compound. Okay, cesium chloride is a compound. Okay, but the same thing, these are ionic compounds. There are so many covalent compounds also. Okay, there are also some metallic compounds also. What we see is when I add, instead of I can take an example. For example, something called nickel aluminum, NiAl. This is a compound which has what is called a BCC kind of a structure. And such a material, if I keep on adding so many elements into it, instead of being a compound, it becomes a disordered structure which has elements inside the unit cell, no doubt, but it does not have a chemical order. For example, in a sodium chloride, every sodium has chlorine around it, every chlorine has sodium around it. Okay, it is called chemically ordered structure. I'm now breaking this chemical order by increasing the entropy of the system and making it a chemically disordered structure. And such a chemically disordered structure has what we found in most of our studies and quite a number of other people, that you can utilize this material as a wonderful material with high combination of strength and toughness, okay, which is not possible with compounds. And that is the beauty of this, such a thing of making it high entropy material. This is somehow people have not done earlier. Never people thought that putting large number of people thought that if I put large number of elements, material will become complex. So I may not be able to study it at all. I may not be able to understand it at all. Now what we see is I put 5 elements into the structure. Still, I mean, I hope all of you know about crystal structures, BCC, FCC, this kind of things you must have heard about. So I have the example that I showed you earlier. It has 6 elements inside it. Though it has 6 elements, when I look at the X-ray diffraction study of that particular material, look at X-ray diffraction pattern, you will see that the whole material is of a simple BCC structure, nothing else. There is no complexity at all. So though there are 6 elements present inside that, it has simple BCC structure. And that kind of a beauty of a simple structures coming out of a multi-component material has never been even thought about it. And now people are excited about it, and people are making variety of that. And not only for applications like this, now we are working on magnetic materials. What happens when I have a simple magnetic material? Take a nickel ferrite. What happens if I dope nickel with a large number of elements and dope iron with a large number of elements? So it will be a nickel ferrite with a lot of dopants inside it. And by putting a lot of dopants, what is called configurational entropy goes up. And if I can make a high entropy oxide, what will be its magnetic property? And that is something which is very exciting. What will be its optical property? What will be its dielectric property? So a lot of people are excited about it to find out whether I can make a newer materials with newer properties with this kind of a combination of elements. And that's something which at least from metallurgy perspective, I can tell you that we have found very exciting properties. These materials have very high strength. We have been, I mean, for example, we are now collaborating with General Electric. We are collaborating with Boeing. All these people are very excited about making high strength materials for aerospace applications. Bhuvana, does it answer your question? I have given a very long answer for a short question.
Such a descriptive answer, sir. Thank you so much, sir.
Anybody else?
Sir, when you were talking about the piezoelectric pellets creating energy, what is the efficiency, sir? How much efficient are they in converting it? And what are all the shapes we can do it?
See, very important thing that you should know in all these kind of cases is, what is important is, am I able to generate something? I'm not doing anything. I'm not doing any chemical reaction, nothing. I'm simply putting a small 1 rupee coin in my shoe and then walking. And even if I generate a small electricity with not so great efficiency, it is still okay, because for a soldier to carry a huge batteries with him, okay, and finding a place where he can charge it, okay, they are all working in places like Siachen, and where for them to find charging stations is not so easy. So these are certain areas where even if you get a small energy, you are happy with it. Okay, so we should not look at from the perspective of whether it is as good as a solar energy or not. These are all certain things one has to be careful in thinking. Okay, yes, maybe energies are not very high right now. People say it is 20%. People are working hard on that to increase that to higher. There are a lot of interesting issues to be solved, and that's where you feel excited that there are so many challenges. Wherever there is a challenge, it's an opportunity to learn, and that's why there is excitement. Okay, so any more?
Good evening, sir.
Yes, madam. Yes, Ranjini.
Sir, what is the basic principle behind the atom probe tomography? Is it a mass spectroscopic technique?
Wonderful. It is exactly what you have said. It's a mass spectroscopy. So simply, time of flight. Okay. If I have an atom of a certain mass, if it is traveling towards a particular detector, the time it takes to travel a certain distance depends on the mass.
Yes.
So what I do is, I make this material in the form of a tip like this. Okay, this is a pen sharp tip, you see. What I do is, at the tip of it, I apply a field, electrical field. And if the field is large enough to break the bonds, okay, and an atom can be pulled out of it. Okay, so once the atom is pulled out of it, okay, I can say it is time t equal to 0 now. Now I put a detector at a certain distance and allow this particular atom to move towards that particular detector and measure the time that it has taken. And from that, I can assign what is the atom. Is it an aluminum? Is it a tungsten? Is it copper? What is it? I can find out by knowing that particular time of flight. And where it is hitting the detector tells me about the XY coordinates of that particular atom on my tip. So I also not only know the nature of the atom, I also know the XY coordinates of the atom. And once one layer of atoms is knocked out of the surface, okay, and they all go and hit the detector, then I knock out another layer of atoms. Okay, one more layer goes and hits the detector. So like that, layer by layer, I am collecting all this information, and in the computer, I stitch all these layers and recreate the three-dimensional information. That's exactly like a CT scan.
Okay.
Okay. So this is the beauty. Only thing is, CT scan happens at a much higher, coarse resolution. Here you are doing at the atomic level resolution. Okay, it's a CT scan at the atomic level, like an angstrom level resolution. That is the beauty.
Thank you, sir.
One last question before I leave, if you have anybody.
Sir, I'm Lokesh.
Okay, two. Okay, Lokesh and one more girl is asking. I will take that after Lokesh. Yes, Lokesh.
Sir, I'm Lokesh from Madras University. Sir, I have a doubt. Is there any limitation to measure the atom using Titan instrument?
In Titan. So let me tell you the difference between Titan and an atom probe. Okay. Why should I have two different microscopes first of all? Titan is called a transmission electron microscope. Have you heard of it anytime?
Yes, sir.
Okay, transmission electron microscope is something like this. I have a sample. I have an electron beam going through the sample and coming out. Okay, and as it comes out, it gives me information of the sample because this electron beam is interacting with the atoms inside the material. So what I see is if there are atoms inside, a projected image of the atoms, how the atoms are arranged inside the material, a projected image, a 2D image, I am seeing it. So transmission electron microscope gives me a 2D image, a projected 2D image, whereas the atom probe gives me a 3D image because I am stitching layer by layer. So that is the basic difference. You can see a 3D. So for example, if I have a sample in which there are different layers of atoms inside the sample and the electron beam is going through, what it is going through, as it goes through, it gives me a composite information. If in these layers I have different types of atoms, okay? For example, if you take a barium atomate, barium atoms are in one layer, titanium atoms are in one layer, let's say oxygen atoms are in one layer, okay? I am getting a composite information here, okay? I am not able to make out what element is what to a large extent, whereas atom probe can give you. And then next one is, you said, what is the limitation, okay? In fact, the only limitation is how well you can prepare your sample. You need a sample which has to be extremely thin for an electron microscope, so that when the beam is going through, it is able to come out of the sample and has some enough energy to give you a pattern, okay? Otherwise, what happens is if you have a thick sample, the electrons, as they pass through the material, there are electrons inside the material, and these electrons will interact with the electron beam, so you lose a lot of energy. At the end, the electron beam that is coming out will have very less energy, and you will not be able to see the image of the sample very well. That is the only limitation. Okay?
Okay, sir. Thank you so much.
One last question. One girl was about to ask something. Who is that girl?
I'm Parvati from Madras Christian College.
Yes, Parvati.
You said about the if we convert the ordered, I mean like crystalline solid in, by doping or something else into a disordered state, it will have high tensile strength, that you said like that. Okay. But what in case of amorphous solid, which is already in disordered state? Very good question.
Yeah, very interesting question. Actually, this is true that as the entropy keeps on increasing, okay, I do not know how much you know about crystal structures. When we talk about crystal structures, you talk about a structure and we also talk about what is called random arrangement of atoms, which is called amorphous, as you just know, said. But between a crystalline material and an amorphous material, a crystalline material can also be chemically disordered. Okay, it is structurally ordered but chemically disordered. What I basically mean is, if I think of a structure, something like sodium chloride, let's say, okay, if sodium and chlorine atoms inside the unit cell, if they are randomly arranged, okay, the unit cell is still there, but there is no chemical order inside, right? So what we can say is, we say that it is structurally ordered but chemically disordered, okay? And an amorphous structure is both structurally and chemically disordered. So if I keep on increasing the entropy, what happens is a chemically ordered structure becomes a chemically disordered structure, but structurally still ordered structure for the in the beginning. And as I keep on increasing the entropy more and more, it will become a completely amorphous structure. Okay, so that kind of amorphous materials also have some important properties, no doubt about it. But there are problems with amorphous structures, that amorphous structures are unstable many a times. They are metastable. So when I heat the amorphous structure, it immediately becomes a crystalline material. So that is one of the problems of this amorphous material. And though it is possible to create, and we ourselves have done high entropy amorphous alloys, we made. Okay. So, but such materials have a difficulty that their application window will be limited. Whereas this kind of a high entropy alloy, which is a crystalline material, but still a chemically disordered material, has much better strength and much better stability. Okay, that's the only.
Yes, sir. Okay, sir. Got it.
Okay.
Thank you, sir.
Thank you very much, Prakash. I think I should leave now. Okay, there's another meeting, somebody is waiting there. Okay, so if you don't mind, thank you very much, friends. Anytime you have any questions, just drop a mail to me, and you should be able to find my email address easily. And all the best to all of you. Okay.